Day 9, smoke basin. Okay, well that's quite short. Now, I'm going to read the problem statement out loud to ensure that I cannot have missed anything. These caves seem to be lava tubes. Parts are even still volcanically active. Small hydrothermal vents release smoke into the caves that slowly settles like rain. If you can model how the smoke flows through the caves, you might be able to avoid it and be that much safer. The submarine generates a height map of the floor of the nearby caves for you, your puzzle input. Smoke flows to the lowest point of the area it's in. For example, consider the following height map. Each number corresponds to the height of a particular location, where 9 is the highest and 0 is the lowest a location can be. Your first goal is to find the low points, the locations that are lower than any of its adjacent locations. Most locations have 4 adjacent locations, up, down, left and right. Locations on the edge or corner of the map have 3 or 2 adjacent locations respectively. Diagonal locations do not count as adjacent. In the above example, there are 4 low points, all highlighted. 2 are in the first row, a 1 and a 0. They're not highlighted for me. Never mind. 1 is in the third row, a 5. Yes. And 1 is in the bottom row, also a 5. All other locations on the height map have some lower adjacent location and so are not low points. The risk level of a low point is 1 plus its height. In the above example, the risk levels of the low points are 2, 1, 6, and 6. The sum of the risk levels of all low points in the height map is therefore 15. Find all of the low points on your height map. What is the sum of the risk levels of all low points on your height map? Well, that sounds potentially straightforward, but it remains to be seen how large the input is. Is that 100 by 100, so 10,000? I'm guessing it's 100 based on the rough length of the line, and I'm guessing it's square because they usually are. So if it is 100 by 100, we'd expect it to say there's 100 lines and 10,100 characters, if there's a new line on every line. I think I'm probably going to read the whole input into memory, although it is not necessary at this stage, because I only need to compare each line to the previous and next line. So I only need to hold 3 lines in memory. And to make life easier, I wonder if we should just surround the entire map by made-up points of height 10, and then we never need to check. We never need to check if we're comparing it against something that's off the edge of the map, because we know we never will. I must do my silent contemplation. The input's quite distracting. Maybe I'll shut my eyes for my silent contemplation. See you in a minute. The input is indeed the size I expected. I don't think I need any more silent contemplation. I think I'm ready. So the width is actually the length of the line plus 2, because we're making up our a little border of 10s. So we want to now right. So we have a 0 at a 10 at the start, 10 at the end. To increase y, we need to go so width at this point refers to the length of the line, but later on we'll refer to the size of our grid. So we want grid y x plus 1 to be equal to lx minus 0. And then, just to be on the safe side, I fancy that we might print the grid out. Ah, no, that won't do the right thing. And I think that'll give us a colon around the edges. During my silent contemplation, I did consider that we could begets straight into the grid and then just operate on characters for the whole rest of the program. But I decided operating on numbers 0 to 9 was nicer. I think I'd like to get this sample input, but I might just give this the real input. Ooh. That's strange. What is 100 hundreds? That's 10,000. Eh? Yes. You cannot allocate infinitely many lots of 102. Well, it looks promising. Oh, hang on, we've put a new line character in our grid. That's a good point, we don't want that. Does the last line of input end 87890? Yes, it does, so that's good. But we need to lose the new line. So we just say width equals that, minus 1. Okay, so we're now reading in the input. So what we want to do instead is iterate over the whole grid. And if this point is a local minimum, then we add up the risk. 100,000 points. Most of them aren't going to be local minima. This I don't think will overflow. So if grid yx is less than we'll say g is grid yx, and then if g is less than grid y minus 1x and g is less than grid y plus 1x and g is less than grid y x minus 1 and g is less than grid y x plus 1, then risk equals risk plus g plus 1. So I'm actually not going to bother extracting the sample input from the problem statement because I fancy that this might be correct. However, if I try to submit it and it says it's wrong, then I should try to test it on the sample input. So we're reading the input now. I can tell because the disk light is flashing. We finish reading the input, and hopefully we get an answer that's not negative. Right then, read the problem statement out loud, followed by 1 minute of silent contemplation. Next, you need to find the largest basins so you know what areas are most important to avoid. A basin is all locations that eventually flow downward to a single low point. Therefore, okay, so my first thought is this will be dynamic programming. You start at detect all the low points like in part 1, and then for every point that's immediately adjacent and higher than that point, you know it flows to that point, and then you spread outwards. So is it dynamic programming? Or we're probably just breadth first search? I don't know, maybe it's still considered dynamic programming. Anyway, getting ahead of myself, this is supposed to be read the problem statement in full. A basin is all locations that eventually flow downward to a single low point. Therefore, every low point has a basin, although some basins are very small. Locations of height 9 do not count as being in any basin, and all other locations will always be part of exactly one basin. The size of a basin is the number of locations within the basin, including the low point. The example above has 4 basins. The top left basin, size 3. Oh, well, this would make more sense in color, wouldn't it? Yes, otherwise all of the basins look exactly the same. So if I look at this though, oh yeah, the top left basin of size 3 is 3, 2 and 1 because those are surrounded by 9s and they flow downwards to the 1. Okay, the top right basin of size 9 is all the points that flow to the 0. So we've got 4, 3, 2, 1, 0. Okay, yeah. The 4 on the second line flows upwards to the 3 and then down to 0. So that's 6 points we've got already. And then there's 2, 1 at the end of the second line and 2 at the end of the third line. So that's our top right basin. And the middle basin, okay, well, I think we understand anyway. Find the 3 largest basins and multiply their sizes together. In the above example, this is 1,134. What do you get if you multiply together the sizes of the 3 largest basins? 1 minute of silent contemplation. Okay. So I think from the point that we add up the risk in part 1, from the point that we add up the risk, instead of adding up the risk, we want to scan we want to, well, I'm going to call it scan basin. And what scan basin will do is scan outwards for all of the points that are within the same basin. Now you know an adjacent point is inside the same basin if this point is lower than the adjacent point and the adjacent point is not a 9. So actually it doesn't matter whether we depth first search or breadth first search for this, does it? Which is good, because during my silent contemplation I realized that I don't have a good data type for implementing a queue. So breadth first search would be annoying. But what I'm going to do is okay. This will say we'll get the basin size here. And then we'll just add it. So we'll scan basin will return the size of the basin at the given coordinates. Finally, we'll sort the sizes. We want the largest first, which means it should be negative when A is larger than B, so we want B minus A. And then we want to multiply together the largest 3. I don't know, answer. And this will be and scan basin can actually overwrite the given coordinate with a 9, and then for each of its neighbours it can so say it's a 1. Actually, if grid yx is greater than or equal to 9, then there's no basin here, basin of size 0. So then we'll say size, well, we just want to mark this point as a 9 so that we never scan it again, and then the answer is 1 plus scan basin x minus 1y plus scan basin x plus 1y plus scan basin x y minus 1 plus scan basin x y plus 1. Now this might be too slow because that's an awful lot of recursion, and the depth of this recursion could be quite high. So how big is the stack frame going to be here? Potentially quite large, because we might have, well, we've got 2 locals, we've got a stashed return address, we've got 1, 2, potentially 4 saved up things. So that's like 7 words per stack frame. We've got a 2k stack. So we can only have 300 levels of recursion. So I'm going to try it, I think. Well, let's try it on the sample input. If it falls off the rails on the real input, then we either need to rethink this or just change the stack size. I've never tried changing the stack size from within SCAMP OS, but I don't see why it wouldn't work. Actually, do you know what? I'm just going to wing it. I'm going to run it on the real input and see what it says. And if it gives a number, I'll submit it and maybe it'll be right. So then there are two ways that this is likely to go wrong. Firstly, it gives us the wrong number, in which case we run it on the sample input. Secondly, it crashes, in which case we increase the stack size and try again. Or actually, if the stack overflows, will it definitely crash? Or might it just give us the wrong answer? Or might it work anyway? It will probably crash, because the stack grows downwards, and the thing just below the stack is the code at the end of the program, and strings. It'll probably crash if it overflows. Well, away we go. Maybe this wants a progress indicator. I could put a dot on every line. Oh, we've got an answer, that's good. Yeah, first try. Nice one. Oh, I feel like that went really well. That was half an hour. So a couple of things. Reading the problem statement out loud, I would say very much helped, because there were some things, even when I roughly understood part 2, coming across the stuff like, what was it? Oh no, it was on part 1? On part 1, it said you have to add 1 to the value of the low point to compute the risk, and I might have missed that. So reading it out loud meant I definitely didn't miss it. And the minute of silent contemplation I found really helpful as well, because not having to narrate my thoughts, they can go much more quickly. So I almost had the program written in my head before I started. So that was really good. Well, thanks for watching. Goodbye.